I would like to, first of all, I would like to say that this school is a total initiative of students. And thank you very much, especially to Anton Svetlichny for his idea, for his initiative, for his leadership in this field. Also, I would like to thank Andrii Semenov and Alexa Kiva for their hard work. Hopefully, our school will have success. Okay, as Volodymyr told already, I'm from Boglubov Institute for Theoretical Physics. Let me say a couple of words before I start about our institution. Our institution is one of the leading research center in the field of theoretical physics in the East Europe. And actually, we have a close connection with Kyiv Academic University. Our Department of Theoretical and Mathematical Physics is closely associated to the Kyiv Academic University. If you are dreaming to have to make your master thesis or your master work in the field of quantum science or computer science, you can join our master programs. We guarantee you high educational standards, and we also guarantee you that your study will be closely related to our current research. You may apply for our programs now, so if you're interested, please join us. Okay, and now I will start with my lectures. So this is the plans of my lectures for today and for tomorrow. First, today I will say a bit about classical physics and classical information. This will be more or less introductory materials. And after that, we will speak about quantum bits and quantum bits that is already a quantum piece, one smallest quantum piece of information, generalization from multi-qubit systems. And at the end, this will be for sure tomorrow, I will say about the most important challenge that can kill everything that we are speaking today about noisy environment. And this is really an important challenge for quantum computing. And this is what we also have to consider in our science. Okay, my first lecture is classical physics and classical information. This will be nothing about quantum. My aim is simply to give you some introduction to show you how physics and computer science can meet together. Yeah, and also I would like, so this is important simply for quantum physics. Yeah, and when we start to think about this, yeah, we are asking ourselves what information is. Just Google it in internet. You may also write for yourself what is your definition of such a category of information. And for example, this is what Wikipedia say about it. Yeah, you can see that a lot of different things for information, very different definitions. And it seems that information depends, what information is, depends on your profession, on your philosophical position, and many other things. And of course, for me as a physicist, it's important what is information from the point of physics. Let's postpone a little bit this answer for this question, and let's try to answer what is another question. What is elementary piece of information? And from the point of physics, this looks like this. Yes, this is just a light switch, yeah, or very similar system. When this is on, this is 1. When this is off, this is 0. This is simply one bit of information, or 0 or 1. If we give more insight, physical insight on these things, we can understand that this is something like a double well potential system. You can consider, if you do not study physics, you may consider this that this is literally some 2 wells or 2 holes in the ground, yeah, and in this hole there is 1 ball, for example. When this is in this position, that is described, for example, by switch like this piece, this then bit has value 1, and when this is in this well, so then this has 0. Okay, and all this means that information is somehow associated with the position of this ball, or we say that information somehow associated with the state of physical system. In quantum information, people also sometimes say that information is the state of physical system. But let's not to be now so radical, and let's consider it step by step. Okay, information actually from the point of physics, this is position and velocity of this ball. Yes, it may have some velocity. It can be here or it can be here. We physicists do not say about velocity, we say about momentum. That is actually product of mass with velocity, but it changed actually nothing for our purposes. Also, for us, it is important that we do not interesting where exactly this ball is from the point of quantum of information. Sorry, this can be here, here, or here. And we can write just rough description. For us, it's also important. Is it in the left or in the right well? When this is in the left well, this can also be here, or it can somehow fluctuate here. So, okay, this is 0. When it is here, the bit has the value 1. Okay, this is the first things, that state of the system. State of the system, this is what we should understand. And the next story, that with time something happens with this system. Okay, when this ball is situated here, this ball or particle, as you wish, is situated here, then we can say that our system is at rest. So x is equal to x0, p is equal to 0, nothing interesting happens. But what you can do, you may apply some external force to it. The physics students know that external, so that such physical systems is described by so-called Hamiltonian equations. So this is time evolution equations. And the central point here is so-called Hamilton function. Yeah. If you do not know, if you are not physicist and do not understand what is it, this is not really now important. But nevertheless, important things is that we can describe, if you know where ball is here, if you know this force, if you know this profile, we can calculate where this ball will be in any other moment of time. And this is actually what classical evolution is. Yeah. Okay. You can apply very interesting force. This can be sophisticated, time dependent. Also, you can consider some frictions or dissipations here. And you can do, for example, such things that if your ball at the some moment of time was here, then after applying this external force, it appears here. And vice versa. If your ball will be here, is here, this after this external force is here. Such an operation. So we do not need to know everything about this for information, this science. We only should know where in which well is here, in the left well or in the right well. And actually you can see that this is the logic gate node. Yeah, really, time evolution, classical time evolution can be considered like a logical operation. This is very important when we consider from the point of physics what time evolution is. This actually logical operation. And we can also apply this situation when we have many bits, many classical bits. And when we use this mechanical analogy and this mechanical idea fusor, we can obtain at the end something like this. So this is a stepbrother of grandpa of the modern computers. They were looking like this, a really mechanical computer. Of course, today we are now using something else, but idea is actually very close to this. Okay, we understand what is classical time evolution. This is for us is a logical operation, and the next step what we should know that sometimes we do not know exactly. So that what what I was talking for you now is called actually not simply state, but a pure state. Pure state means that we have exact knowledge about x and pi, about position and momentum of this particle. In the rough description, this is simply exact knowledge of the well where it's situated, left well or right well. Okay, but it can be that we do not have such knowledge. It can be that that in some reasons we cannot control our system very good. We do not know where it's situated. In this case, physicists say about mixed states. Mixed states in classical physics is a probability distribution, rho from x and p. So this is probability density, or sometimes called as Liouville function. In our rough description, this can be simply a probability of where the particle is situated. For example, this can be such a function, rho m, with the probability p. This is situated here, and then this is the value of bit 0. And with probability 1 minus p, it's situated here. Then this is in the right well, yeah? Then this is the value of bit n equal to 1. Okay, so maybe we have some question in chats. Maybe I will answer them. Okay, it's not accessible to me now, but after lecture I will try to answer it. And okay, this is simply what we say. We say as a mixed state of a particle. But the state itself means actually nothing. This is simply letters. This is simply mathematical symbols. Because even if you write classical evolution for the states, because what you need to connect it with our real physical worlds. In classical physics, this looks very similar, very easy, because really this is not a big question where this is really situated. Here to see, look here and here, but this is quantum measurement. This actually quantum measurement, and we not quantum, but classical, sorry, measurement, and this measurement should be performed. So measurement, in order to do measurement, you need a measurement device. Measurement device can be, for example, a lamp. When it's on, you should see when your switch is on, you should see the light. But something wrong may happen with your device, on something with your measurement device. For example, your lamp is broken or something in electrical circuit, and you may see this light only with probability, which is written like this, P1 given 1. So probability to get value 1 to value of qubit 1 under conditions that its real value is 1, and we will mark it as Q1. And with some probability 1 minus Q1, you will not see the light, even if your real state's in on. This may happen. This is simply imperfect measurement device. The same story may happen if you have the state 0. With probability Q0, you will see no light. And this means that everything is okay, but something may happen in your quantum circuits, and with probability 1 minus Q0, you will see the light. This is simply an imperfect measurement device. And you see that measurement device is actually described by some function pi 1, 1, 0, 1, 0, 0, P1, pi 0, 1. And this function has 4 values. And in classical physics, it's sometimes called as a response function of the measurement device, Pk given n. This is probability to get the outcome k given the state n. Okay, this is already something, but how this is related to the probability distribution of the measurement outcomes? If we have some state rho n, mixed state, and we know characteristic of our measurement device, we can calculate this probability with such a rule that is actually the law of total probability. So probability to see the lamp, to see the light or do not see the light, is simply sum with response function and this probability distribution, which represents the state of our classical system. It's very important relation because this relation we will see further in our classical studies, in our quantum studies. Okay, analog of these things. But this, you can see, includes now two components. So the outcomes depends on two things. It depends on the state of the system, and it depends also on the measurement device. Okay, let's go to summary for this. I will do summary for this short lecture. First of all, that this is important things so that you should now you should study from all this short information. First of all, I would like to you understand that pure state in classical domain is simply numbers n. This is numbers. Yeah, this can be real numbers or a couple of real numbers, also complex numbers sometimes we say. But nevertheless, this is simply numbers. Mixed states is probability distributions associated with these numbers. So here we have pure states. We have complete information about our system. Mixed states when our information is not enough. Okay, measurement. For measurement is always characterized by a response function, pk given n. A complete similarity with this will be in quantum domain also. Measurement and states can be combined, and they result in probability of the measurements outcomes with such an equation. And the last but not least is that time evolution can be presented as a logical gates. So this is somehow the end of this short introduction of my short introductory lecture. When some students have some questions and moderator allows, so maybe I have a bit time to answer them. Vladimir?
I guess we have some questions
yes.
in chat.
Sure.
Yeah. Do we have some question?
There is one question in chat.
Yeah. Do you understand? Okay. Do you understand correctly that we discuss probability distribution within the non-quantum distribution? Yes, exactly. All that I told you now is classical system. All that I told you up to this moment is classical system. Since classical system, we have students which not only physics students but also computer science students here. Students who never studies maybe quantum mechanics, and this is why I would like to make some connections and bridge with well-known things. This is actually a summary that you can look and that we will need for our future applications, for our future studies. Okay, we do not have another question, other questions.
There is one more question actually,
okay.
From Nikita.
Yeah, but I have answered this question, I believe, already. So I have answered this question. Yes, this is about classical physics and classical information. Okay. When we close this case, let's go further and to the second part of my lecture. And this is already about quantum bits, or what is quantum information. Okay. In quantum, so in classical domain, I was marked these the 0 and 1, the states, the values of bit 0 and 1 with such square brackets. Now we will mark them like this. This is called ket vectors. We will talk about it even further, but this is in quantum information, very similar thing. What is very important? So now let us consider that this is not a classical device, this is quantum device. For example, this is very small device. Again, in such a potential, for example, so it's still possible to create. What is interesting physical observation of physical results? If we have our ball here, if we have our particle here in some time moment, it is possible that with time, in the next moments of time, just a moment, something happens, with time evolution, there is a non-zero probability to find it also here. This is almost unbelievable, since it looks like this particle comes through this barrier. Actually, in physics, this is what we call tunnel effect. And this is very important now that this particle is situated in two these wells simultaneously. Yes, you have a probability to find it here, and you have a probability to find it here, but our future studies has shown that this is not mixed states. This is not simply a some stochastical force or some unknown thing. This is still pure states, yes? And this is such interesting pure states that our particle or our bore is situated simultaneously here. What we want physicists, what we want to describe it, what we are trying to describe, we want to write something like this, that this is some number C0 multiplied with this vector 0 plus C1 and 1. But do not consider that this is simply 0 plus 1 multiplied with these large numbers. This is actually something else. And the most important results in quantum physics is that pure quantum state of qubit is already not a number. This is already a vector in 2D, in 2 dimensions. This vector can be written down as this column, and an important thing is that components of these vectors are complex numbers. So first important things, first important difference between classical and quantum physics, and actually between classical and quantum information. Pure state of a single qubit is now not a number. This is not 0 and 1. This is a vector. This is a vector with complex coordinates. Please do not think that this is a vector in a real physical space. This is not true. This is not a real physical space. This is some Hilbert space of states, some abstract space where quantum states live. And it is not related to our real physical world, to our physical space. So this is the first important things that I would like you to study from this lecture. Another story, that these components, this vector, should be normalized. So its length, if I can say about length for complex vectors, but nevertheless, its length should be equal 1. So these coefficients C0 and C1 are not really arbitrary, but such that this relation should be satisfied. So C0 module square plus C1 module square is 1. Well, the next point which we should study, 0 and 1 are also vectors. And these vectors actually form the basis in this Hilbert space of qubit states. And at the end, we can say that our arbitrary pure state, I would like to say that this pure state, not mixed state, at least so we have some probability things here with probabilities, but this is still pure state of quantum system. We will write it like this psi, and we call it as a ket vector. Can be written like this, C0, 0 plus C1, 1. Since 0 and 1 are basis vector, you can see C0 and C1 are coordinates of this vector. You can see that this very obvious relation from the standard school geometry. But now this is not really geometry. This is something more. This is quantum physics. So what we have studied from here and what is totally differs, how totally different quantum world from the classical world is that quantum state is already a vector. A vector with such a restriction, quantum state is a single qubit, I mean, with such a very important restriction, and with complex coordinates. 0 and 1 are just bases in some space of states. Okay, let's study more, because as you have seen from my classical part of the lecture, we should study what is states, what is time evolution, what is measurement. And now we will go a little bit more with state to study what state is. Okay, our vector is looking like this, and we have from this vector such restrictions. But when you see on such restriction, you can say that, oh, stop, this means that I do not need now 4 numbers. I need just 3 numbers, because 4 numbers, 2 numbers, real numbers here, 2 real numbers here for each complex number. I now need 4 numbers, no, don't need 4 numbers because one constraint exists. Okay, this means actually that you can write another parameterization. You can introduce another parameters, not C0 and C1. They are somehow inconvenient for us. You can present another parameters. Look what I have done. I have represented 2 other parameters, theta and phi. You may ask me where is third parameters, because it was 2 and 2, and this was 4 minus 1. This should be 3. I will answer this question you a little bit later, but now it's interesting for us that, look here, by representing new parameters, theta and phi, I can write for these coefficients in another form. So C0 is now cosinus with theta divided by 2. C1 is ye phi sinus theta divided by 2. Also, another parameter should exist, but this parameter can be considered as a global phase. And global phase does not play any physical roles, just accept it as it. And we will, in the next part of my lecture, you understand why it happens. So only 2 parameters is enough to completely describe pure state of qubits. These parameters are theta from 0 to pi and phi from 0 to 2 pi. But now, if you look at this parameter, you can understand that something happens. This is something very familiar. This is something that you can be very familiar. Yes, this is a sphere. This is a sphere, and this sphere is called as Bloch sphere. So any quantum state can be described as a point or a unit vector, yeah? But this is the same. In such a space, X, Y, and Z axis. This is very conditional designations. Please do not consider it as something related to the real physical space. This is not related to our configuration space. Sometimes, by the way, this is related, sometimes for some qubit states, but typically it is not related. This is only very conditional denotations, yeah? And our quantum state is actually a point or a unit vector on the Bloch sphere, which is characterized by the angle theta and by the angle phi. Okay, qubit states can be characterized by a vector with such 2 angles. I see some questions in the chat. Vladimir, can you help me?
Yes, I can read them to you. You answered most of them by this point, but still I'll repeat some of them. For example, question from Khulud Ali Al-Zabi. If we do have 128 classical bits, how many qubits do we need?
I will answer you. If we do have 128 classical bits, a little bit later in the next lecture, I will answer this question for you. Because now we are concentrating only with single qubit, but very interesting question. Thank you very much. Just have a patience up to a bit later.
Another question from DTP Kulinski. Can be classical measurement state response function nonlinear?
I don't know what you mean really nonlinear. If you say, so actually the response function, what we have this question, this is this rule, this is a law of total probability. So then relation between probability and conditional probability is of course linear. When you mean nonlinear, that this is dependence on the chi and n nonlinear, yes, it can.
And there are also questions about, from Lysenko Ivan, what is the correct definition of qubit, but you just gave
This means very interesting written, qubit, like this is classical, not with Q, but with C. So classical bit or quantum bit. So qubit is a quantum system. Qubit, when you mean quantum, so when this is not, so let's see that this is a typo, yes? Qubit. Qubit is a quantum system, actually, is state, or we can say a quantum system, two-level quantum system. Quantum system that has two basis states. The system which can be described by a two-dimensional complex system. This is actually qubit. But we can say about qubit state. Qubit state, this is the vector itself.
There is another question related to this, if we can call it a quantum state.
Just a moment. The next question. What do you mean by states 0 and 1 exactly? What do you mean by state 0 and 1 exactly? Very good question. Very good question. What do you mean with state 0 and 1 exactly? Maybe you should, so this is a very, I would say, philosophical question. In this domain, you can say that here exists some state, so which we say like a 0. This is very abstract notion. Nature looks simply like this. And the state 0 means that particle situated is totally here. But this is not enough, of course, because can be some situations that, this is here, but somewhere in this well, but where exactly we do not know. Yeah. So what I mean that 0 and 1 exactly, so states 0 and 1 exactly, this is just, let's now consider it from the our pragmatic or formal point of view. This is just elements of some Hilbert space, of some vector space. Physically, this means that when this is in state 0, you have a 0 probability to find it here. When this is 1 in state 1, you have a 0 probability, a probability 1 to find it here. So when state is 0, with probability 1, you find it here. When state is 1, with probability 1, you find it here. But this is only a rough question because some issues may happen. Now, please consider it only very formally. That quantum mechanics does not have a really good connection with our intuition. This is the problem. We do not have, so in classical physics, we have intuition, we have very good intuition. In classical physics, intuition usually does not work. So this is just two elements, that's just two basis vectors. So state is now a two-dimensional vector, complex vector, okay?
There was, thank you for your answers. There was another continuation of previous question about qubits, if they can be called quantum states.
Is a double well potential suitable for physical implementation? It may have more than bound time. Yes, it can. It may have. We will talk about it. This is just a demonstration. For sure, you're right. It may have more than 2 levels. For sure, you're right. This is just a demonstration, nothing more. Okay, so about physical implementation, I hope to speak a little bit later. Okay, let's go. Let's go further with my lecture. And now we go to the next part, time evolution. So when I say that my physical state is a point at the block sphere, what may happen with time? With time may happen everything you want, but the new state should be still in this sphere. So any rotation, any of this vector are possible as a time evolution. For some reason, we call it unitary time evolution. You will understand now, but this unitary vector should still be unitary vector. And this, when this is a point on the block sphere, this should be still a point on the block sphere. This actually what happens during time evolution. So vector was here with the angles phi0 and θ0, and after that it's here with the angles phi from t and θ from t. And this is, yes, it was initially the state c0. After that, this is the state c from t. Okay, very easy, yes? But how to describe it? Now let's consider that our time evolutions, our vector at the end. So now we start with mass, and mass will be a bit, sometimes this will be easy, sometimes it will be quite complicated, but sorry, this is quantum mechanics, it does not work without mass. So at some times, initial time, we have such vector with such positions. For C1, we have cosine θ0 divided by 2. For C0, for C1, E if phi0, C sine θ0 by 2. After evolution, we have another vector, psi from t. They should be somehow connected. How to get one vector from another vector? There is a very important, a very famous result in quantum physics that everything that's possible is in quantum physics are linear operations. Nothing more than linear operations are possible. Then we have only one chance that we should multiply it with some matrix, U from T, with such matrix elements. But this is not an arbitrary matrix, because this matrix should preserve the length of this vector. This means that this is a unitary matrix. Unitary matrix means that inverse matrix is a Hermitian conjugation. I believe that many students know that what means Hermitian conjugation, but for some students, I just remember that this is transposition and after that complex conjugation. So when this rule is satisfied, then we have unitary transformation. And actually, any such matrix can be physically implemented. This calls unitary time evolution or a unitary logic operation, actually. Any such, so we can always do with our system something in order to implement any of such operation. But this is very theoretically, of course, because in practice, this is not so easy when we do it with quantum systems. Okay, let's now consider some example. And as I told you before, that classical bits, with classical bits time evolution, this is some classical logical operation. Now we consider quantum logical operation. And first quantum logical operation is the NOT gate. NOT gate, this is a unitary evolution. This means that when you have 0, you have 1. When you have 1, you have 0. And this is described by the so-called Pauli X gate, which is called NOT gate. This is actually rotation on the angle pi around the zx axis. So this matrix, this very simple matrix, represents the rotation on the angle pi, p, around the x-axis. Look how we caught. When it was here, this means at the position 0, after application of this gate, and this gate is marked by different in different ways. So I have written for you both of them. Sometimes it's written sigma x, sometimes it's written x. Yes, so I will write both. I will use both designations, but in different places. Please see what happens when it was 0. After application of this gate, it becomes 1. When this is 1, this is 0. And this is in both cases, you can see that this is rotation on angle pi around the z-axis. In both cases, yeah? It was here, rotated, appears here. It was here, and after rotation, you have 0. So you can write that this your matrix or operator, in quantum physics we say also about operator, sigma x. It acts on the vector 0 and it appears 1. It is written, there is now I will present you an element of quantum circuits. So when we build a quantum computer is actually collection of such operators. Yes, of such operation, of such unitary operations. And when we write such a collection, we need to write some circuits, some schemes for this. And this is an element. So how to mark this mathematical notion in another? So there is 2 types of how we can write it. It was the state 0, and after application the gate x, we obtain gate 1. It is now written like, it is also written like this, because this is like a logical knot. So gate x and gate logical knot is the same. So from 0 you can get 1 in the scheme. This is element of quantum, and it calls quantum gate x. The same story from 1. When it was, for example, 1, you act with sigma x and obtain 0. 1 x, so it was at the input here, the state 1, at the output you have 0, and just an alternative designation for this gate. So these gates on schemes can be shown in 2 different forms, like this and like this. Okay, but another 2 gates are so-called Pauli gates, because students who have studied quantum mechanics already understood that this is something related to Pauli matrices. So this rotation simply about around another axis. And you're right. Another Pauli gate is Pauli Y gate. Pauli Y gate is a rotation on angle pi around the y-axis. This is written like this. This actually a Pauli matrix sigma 2, yeah? And this is written like this. So in circuits, we will write it like this, y, simply y in such square. Okay, and another gate from this series of Pauli gates is Z gate. This is just a rotation on the angle pi around the z-axis. So it's represented by such a matrix. And in quantum circuits, you will see such things. So you will understand what this means. Yeah. Okay.
Sorry, there are a few questions from the chat.
Yes, just a moment. I can answer a few, but okay. First question is, any quantum states of two-level quantum system can be mapped into block sphere? Pure states. It's only about pure states. So in quantum physics, the same story is that like in classical physics, there are pure and mixed states. Yes, pure states can be mapped on the Bloch sphere. Any pure quantum states, when you have complete information about your quantum states, you can map it as a point on the Bloch sphere, on the surface of the Bloch sphere. What happens with more general situation, we will talk tomorrow. So, if Bloch sphere is a way of parameterization of coefficients of linear combination, which are both complex of states 0 and 1 under normalization, one does the first coefficients is real, is because we don't. Okay, I understand the question. One more, I believe I answered it already, but let's go again to this story because this is important. Yes, you can write here ye, I, he, and this will be 1, 2, 3 operation exactly as you expect. Exactly as you expect. What is the question? You now may write it in such a form like in brackets and put ye, I, high, this first phase in the brackets. So you will have some common phase, and here still cosinus t over 2. Here you will have I and phi minus he. That is a new simple vector can be written down. But the point is that common phase does not play any physical role. So this phase, the common phase for the vector, does not play any physical role. We will tell about it a bit further in the next. So, do Y and Z gates have their classical counterparts? Very nice questions, because you see, I'm from the community of quantum physicists that have for this question some a little bit different understanding. So maybe my answer will be very, very special for this situation. In principle, yes, I can answer that they have classical counterparts, but let me answer again your question in more details, maybe a bit later, what this means, classical counterparts. Because when you see it just like as this, so it does not, it looks like they do not have classical counterparts. However, there are some, especially for this Y game, but the situation, in my opinion, is not so easy. Okay, because, for example, why, so this is, actually, you can say very formally that, for example, when you have some 0 and 1 vector, and it was when 0, this again 1, but with some phase, and this again 0 and 1 phase, so this has classical Ford counterpart since phase does not play any role. But the question is really deep, and this is connection between classical and quantum mechanics. And for qubits, this is not so easy. Yeah. So this is I would discuss this question very separately. Okay. So quantum computing is just classical matrix calculation with a little bit of Q states interpretation of complex vectors. Yes, in principle, quantum computing is just like a matrix calculation. You can consider it like this, but the most important feature of quantum computing is that this matrix can be so large that no classical computers can model it. Okay, let's continue. I still have some 10 minutes, and I will say about another gate. This is so-called Hadamard gate. Hadamard gate is also rotation on the angle P, but around some other axis that can be written like x plus z divided by √2. So this is something like this. So this is written by such a matrix, H 1, 1, 1, -1. Okay. And let's consider a little bit more what Adamar gate make and why it can be sometimes considered as a non-classical bit, non-classical operation. When you take, for example, this vector on the block sphere 0, and you apply here, so act on this state with 0 state with the Adamar operator, this will be superposition. Superposition means that you simply rotate to this point from here to here under action of Adamar vector. This will be written in quantum circuits like this. 0 is Adamar operator, and after that you have such states. 1 over root 2, 0 plus 1. And another situation, when this was in the state 1, you will get very similar state, but a bit different, because this rotation will be here. This will be rotated about this axis. This x is somehow like this. I don't know if you understand in 2D, 3D dimensional axis, but nevertheless, this will rotate and you will get such a gate. So you have one Adamar gate. Oh, here is misprint, since here you should get minus, also sign minus. Sorry for that. It sometimes happens. Okay, the next gate is general rotation gate. General rotation gates, this is rotation on the axis. So first, we can consider rotation gates. Rotation on arbitrary angle delta around the z-axis. Actually, when you look at this equation, you will understand everything, because you see this only change the phi, angle phi on the delta. When you apply it for our vector, your phi will be now phi plus delta. Formally, it can be written in terms of these Pauli matrices, yes, like this, this exponent minus e delta over 2 delta z. This will actually be this matrix. There are another rotation gates. Rotation gates on the angle delta around the x-axis. This is a little bit more complicated matrix, and this looks actually like this. And of course, the next part of the story is rotation about the y-axis. This looks like this. So 3 rotation matrices, rho z, rho x, rho y. Okay, this is rotation gates. Some important features, so I should mention some important things about these matrices. First, partial cases. There is so-called this is for rho z case, RZ rotation, for this phase rotation. One important special case is when you make this rotation on the angle pi over 2, and this will be such a matrix. This is called S gate. I believe you will meet these gates in your studies at these schools. So please make notes, because this is really important things. And another gate, is called, this is just, again, phase rotation, but with angle pi over 4. And this looks like this. This gate is called T gate. Okay. One more important thing about this rotation gate is so-called ZY decomposition theorem. It turns out that any rotation, any quantum operation with a qubit can be decomposed as 3 rotations. First, we rotate about the z and 4 numbers. First, we rotate about angle, about axis z. After that, we rotate about axis y. And after that, we again rotate about axis z. And some phase, which is physically unimportant, should be also here. So 4 numbers, alpha, beta, gamma, delta, can represent this unitary matrix U, and any operation, any that you can imagine, can we present it in such a form? Just 3 rotation. First rotation about z-axis on the angle delta. Second rotation about y-axis on the angle gamma. And again rotation, but on the angle beta around the axis z. And some phase, of course. Okay, this is what I believe I should stop with this part of the lecture. Let me maybe answer some questions from the chat. Vladimir, can you help me?
Yeah, I can read you the questions. Let's start from here. Why do we look for angle pi a lot? Why this angle is so important? Well, it's
look here, some questions that I see here are interesting, and I just invite everybody to the next lectures to answer this question, because we're particularly about building of Hadamard gate from X1Z, about let me answer more, because Danilo Yakimenko, my colleague, will refer to all such things. So I simply do not want to make now his job, not because I don't want it in fallback, but I believe that he will do it better than me. So any gate is practically a rotation in the or inversion. It is every gate corresponds to some unitary operator on a block sphere. Yes, any gate corresponds to some unitary operation on a block sphere. Qubit states can be one mapped onto states 2-dimensional classical. It seems that qubit states can be mapped onto states 2-dimensional classical oscillator, because every trajectory is encoded by 2 complex numbers amplitude. Maybe I will speak about this in more details, even more, not only harmonic oscillator, you see, it's even more, so of course you can qubit, so the question is either you can describe qubit with classical mechanics, with classical notions, for example, with classical computers. Yes, you can. Single qubit, there is no problems to describe it classically. This is really interesting question, because these angles theta and phi represent so-called phase space for the qubit, and you can represent as simple as some rotation on the sphere. So there is a lot of classical analogies, but as I say, fusers, there is 2 important things that you should consider for quantum mechanics. First, qubit is very simple system, and you should not conclude everything only from the physics of qubit. When you start to consider more dimensions of the Hilbert space, you will get for sure new physics, and you still have a possibility to describe it classically, somehow some possibility to describe it classically, but you may need a lot of resources for this, for example. And another story, when qubit to describe classically, when your qubits are separated, when you have not 1 qubit, but 2 qubits, they're separated in space, you can still describe it classically, but for this purpose, you should consider that special relativity is violated. Sorry. So this is actually the essence of Bell's theorem. So either special relativity, or you should not consider classical description. This is an important, or local realism, what we say. Either it's local, either this is, or this is realistic. This works for qubits. This is not the answer of my talks, but nevertheless, this is very interesting topics. But answering your question, either we can describe one qubit classically, of course. You can use classical computer, calculate everything. When you can do this with classical computer, this means that you can describe it classically.
One more last question.
Can you please explain what is a phase rotation operator? Phase rotation operator looks here. So let's consider it on, oh, I don't have a lot of time maybe, but look on this example. Look on this very easy example. Yes, this is rotation operator, phase rotation. So look at this example. When you act with this on this vector, so the second component of the vector, just a moment, let me find, because I don't have a possibility to write, sorry, maybe. Oh, this is second component, or it's written here, second component. This means that when you multiply it with this matrix, this will be phi 0 plus delta. So this is rotation, just a moment, rotation on the angle delta. And this is just a phase rotation operator. This is unitary operation. Okay, so I don't see.
Thank you. Yeah, there are no more questions. Thank you for your very nice introduction to this topic. And I think we make a lunch break now and return in 30 minutes.
Okay, see you a bit.